Yes, there we go. We can start the session. Enjoy.
Oh, all right. Welcome, everybody. Good morning, good afternoon, good evening, good night, whatever it is. Welcome to parallel session 2 out of 2 for LISA Astrophysics. My name is Gijs Nederlands. I'm an astronomer from Radboud University in Nijmegen in the Netherlands. We have a very full session, so we will start very soon. But before we do so, let me introduce this session. We have a very diverse lineup. We start this session with 3 talks by Shen Chin, by Sophia Yi, and by Shuyan Lao on different aspects of astrophysics, and we'll come back after a break. As many of you will by now know, please ask your questions in the chat at any time. We'll only look at them at the end of the presentations. You can also add your questions in the live stream chat. This will be monitored. I think that's everything to be said before we start. So without further ado, let me introduce the first speaker. Shen, please go ahead, share your screen, which is Shen Xin from Columbia University, talking about ultra short period massive black hole binary candidates in LSST, as these are verification binaries. All right, go ahead.
Okay, thank you for the introduction. So let me know if you can see my slides in advancing.
Yes, and we can hear you. So go ahead.
Great. Okay. Thanks for the introduction. My name is Chengcheng Xin. I'm a graduate student at Columbia University. So thanks for the organizers for giving me the chance to present my short project. So this work is in collaboration with Zoltan Hyman, also at Columbia University. And our work is trying to predict the number of massive black hole binary candidates in LSST and the number of binaries that we would see in LISA as verification binaries. I'll explain what this term means in the upcoming slides. Okay, so we all know that LSST by Vera Rubin Observatory is going to launch in the mid-2020s, hopefully. And among many of its benefits, it's expected to discover a large sample of quasars, likely in the order of tens to 100 millions. So, and as we know that quasars are triggered by merging galaxies, so almost all of these LSST quasars might be powered by inspiraling massive black hole binaries. And among these quasars, a tiny fraction of these could be eventually evolving into the LISA millihertz frequency bands. And as it turns out, I'll explain later the reasoning, most of these have ultra short periods, typically of less than a day. So we call these quote unquote verification binaries. You can think of them as analogous to the galactic white dwarf binaries, which we know LISA would catch, but they're obviously different because they're massive black hole binaries. So the goal of this work, the first goal of this work is to compute the number of quasars predicted in LSST using the quasar luminosity function. So for this, we use a recent work by Garish Kulkarni et al. 2019. We use this work because it's a very large compilation of quasar data from almost all of the major optical surveys. So their quasar luminosity function takes the form of double power law, which is characterized by 4 parameters. So here we have the normalization parameter phi star, a breaking magnitude m star, and 2 slopes, a bright end slope and a faint end slope, alpha and beta. So all of these 4 parameters are redshift dependent. So to get a smooth quasar luminosity function, we interpolate these 4 parameters at 50 values of evenly distributed values of redshifts. So finally, quasar luminosity function can be quasar luminosity can be directly related to the black hole mass under some key assumptions, including but not limited to F Eddington equals to 30%. We also assume a standard quasar spectral template. And last, we assume that the fraction of quasars associated with massive black hole merger is approximately 1. Okay. So these are the first set of results from the interpolation. Our results are in the solid black curves. So this plot shows the number of quasars in LSST as a function of redshift for 11 different magnitude bins. So for comparison, we also add the numbers predicted from the fiducial Kulkarni et al. Luminosity function in the dotted black, and also the numbers presented in the LSST science book. So that's the dotted blue line. As you can see, most of these curves agree with each other, especially in the most relevant region, and that's between redshift 2 to 3. However, for the fainter magnitudes, due to the lack of data coverage, the data coverage is very insufficient for the fainter magnitudes. We had to extrapolate the quasar luminosity function to get the estimates. And finally, I want to mention these sharp cutoffs are just due to selection effect in the original quasar catalogs being used to obtain these luminosity functions. Okay, and so just to summarize the last page by words, from redshift 0 to 7, we predict that LSST can identify 20 million quasars, assuming a single night LSST exposure, and that is from I magnitude of 16 to 24. But if LSST is able to collect their data to lower the detection limit down to 26, we might be able to expect 100 million quasars. But there's two important points that I want to bring up, or two important caveats, as you may call it, that's relevant to this number. So first of all, there are uncertainties that comes into N, and most of this uncertainty comes from the uncertainty in quasar luminosity function. And also the lower detection limit of LSST can be achieved, but it's a little bit harder to achieve by co-adding the light curves over a longer period of time. So these 2 points, I don't have enough time to get into it in this short talk, but I encourage you, if you're curious about either of these caveats, you should check out the paper for the corresponding discussions. Okay, so we finally get to LISA. So the goal is to find the number of compact binaries that could be caught in LISA. So for this, we use the LISA signal to noise. I'm assuming you all have seen this curve in some form. So here I use the curve from Robson et al. 2019. I also demonstrate some evolution of binary black holes with primary mass of 10 to the 7, 10 to the 6, and 10 to the 5 solar mass, where I assume the binary mass ratio is 0.1. So in each of these 3 tracks, the redshift are 1, 3, and 5 from top to bottom. And the diamonds, I believe, from left to right are 1 year, 1 month, and 1 day to merger. So for the binaries to be caught by LISA, or eventually evolve into the LISA band, it has to be above this curve. Otherwise, if it falls below in the region, in the orange circle, it could be caught by, it could be identified as LSST sources, but it wouldn't be caught by LISA. So just for reference, I pointed out the observed frequency corresponding to a period of 1 day. So another important assumption in this is that we assume at least a lifetime of 5 years. And this could be obviously stretched out, hopefully up to 15 years, depending on how long LISA flies. And that just comes from the fact that LSST launches in the mid-2020s and LISA launches in the mid-2030s. So this just means the time that the quasar is caught in, that the quasar is detected in LSST has to be 5 to 15 years prior to the LISA detection. So to find the exact number of verification binaries, so the verification binary just refer to the ones that we're able to catch by LISA above this detection curve. So to find this number, we assume a very simple model. So the fraction of LSST quasar that will enter the LISA band is simply scaled by a fraction of Tm over Tq, where Tm is the time to merger, and this follows the concept that I just introduced, which is LSST should catch the quasar in the last 5 to 15 years of its lifetime. And the lifetime of quasar is on average 10 to the 7 years. So it follows simply from this this fraction that the number of verification binary is just Tm over Tq times n cursive n, the number of quasars in LSST. Okay, so the number of verification binary here are presented as a function of redshift and black hole mass, which is directly converted from the magnitude. And this is the most ideal case scenario where we assume a time to merger of 15 years. So TM equals to 15. So most of these binaries are concentrated in a region from redshift 2 to 3. And this is consistent with the fact that the quasar luminosity function actually peaks at z equals to 2 to 3. And also most of the sources have are on the lower mass end. So from 10 to the 5 to 10 to the 6 solar mass. And this is because the faint end of the quasar luminosity functions are very steep. So in fact, how many quasars were able to, how many binaries were able to see as verification binary depends mostly on how deep LSST can go. So the detection limits, as I marked with the black and the 2 gray lines, corresponds to the single night exposure of 24 and down to 26, which is possibly the lower limit that LSST is able to achieve by co-adding the data. So depending on the lower limit of LSST, we might be able to get 30 to up to 150 verification binaries in LISA. So this plot just shows n as a function of z and m, but it's also a function of period, which in my opinion is also a very interesting parameter. So in the last page, we saw the ideal case scenario where TM is 15 years. So here on the right-hand side plot, I calculate the period of, these are the distribution of the periods of these verification binaries, and also for the least ideal scenario where TM equals to 5 years. But in either of these distributions, we see that the majority of binaries have really short periods, typically within 1 to 2 days. And you can see this more clearly in the zoomed in figure on top. So what does this mean? So this is a very interesting result to me, because overall we see that from this work, we're able to see a handful of ultra short period massive black hole binaries in LSST among a very large group of quasars in the size of 10 to 100 millions of quasars. So these are what we call the needle in the haystack quasars. And what's interesting to me is with years of observation, we might be able to see the evolution of periods, possibly from days to hours. And this is a very robust evidence for the existence of these verification binaries, because this would be during the gravitational wave driven phase of these massive black hole binaries. So this comes to the end of all of the results. Oh, and one more thing I wanted to mention is that obviously this is the most ideal case scenario. In reality, LSST has to try way harder to identify these short period binaries, especially since we can see the evolution of the period even over a few years of observations. So to summarize the talk, first of all, we found that LSST can discover 20 to 100 million quasars with masses of typically 10 to the 5 to 10 to the 9 solar mass, and redshift from 0 to 7. And among these LSST quasars, 10 to 150 of these could have ultra short period and could be detectable in LISA if they were caught by LSST in the last 5 to 15 years of their lifetime. So to make the result better or to improve on the existing quasar luminosity function, we need just better faint end slope for the quasar luminosity function, either by obtaining more data or develop a more a better statistical extrapolation for the luminosity function to reduce the statistical uncertainty in the luminosity functions. And next, we can also co-add the LSST data to search for more fainter sources with ultra short period. So next, I pointed out the needle in the haystack problem, which comes in a bonus in this project, that if we see the chirping of the period for these verification binaries, we could, if this is a robust evidence of the existence of these binaries. And last, which I have not mentioned before, is that given existing LISA detections in the future, or even any sort of sort of evidence of LISA alerts could reverse this work, and they could guide the search of periodicity either in the archival LSST data or any other major upcoming surveys with electromagnetic signatures of the quasars. And that's it. So thank you for listening. If you have any questions, either you can bring it up now or ask me with email. I believe it's on the program.
All right, thank you very much. Well timed, plenty of time for questions. I already see a first hand. Astrid, please go ahead. If you can unmute. Yes, you can.
Yeah, yes. I find this very interesting. I don't know much about massive black holes, so I'm just curious, how long do you think LSST will need to be observing before we start seeing the first of these candidates? And then the follow-up question would be, if we actually want to find them, which is a major challenge, is this something, you know, someone from the community needs to do with all the data set and somehow make it work? Or could we include some of these searches in some of the LSST brokers, for example? Because I know some people are working really hard to make algorithms that actually search for things efficiently. I don't know how they work, but I wonder if we could include this over there.
Yeah, so there's two directions that you could go. I think I could answer both of your question at once. Let me try that. So the first one is, first of all, I pointed out to identify the period of these short period quasars is challenging in the first place. The quasar with shorter period can actually be harder to confirm than those with longer period. I think LSST right now plan to have 3 exposures per night. So this is already longer than the predicted verification binary period that we're looking at here, which is hours. So it would require a lot of co-adding to confirm the periodicity, but we can't have too many data so that we introduce additional statistical uncertainty. So that's something I guess LSST scientists could do. And then in the reverse direction, I think once LSST identify these, could have some of these quasars could have the short period and the mass that's within the range that we roughly predict here. We could say that, oh, these could be potential LISA sources for LISA to point in the future. And in reverse, if we identify something in the LISA detection, but we're not able to, but we weren't able to focus on these in the LSST catalog, we can use that as a reverse search for their ENM signatures in LSST or other surveys.
Thanks.
Yeah.
Are there any other questions? I don't see hands or anything in the chat. In the meantime, I had a question. Suppose we find the periodicity, do we immediately have some idea about the masses, I guess the distance, yes, but also about the masses of the black holes? Or would that be unknown and we need to get the F dot or the period change to get the masses?
So the mass can be inferred from the luminosity as a first step if we know the redshift. So that's directly how I would, I guess, obtain the mass. Yeah, I'd say we would directly know the mass.
Okay, that would be great.
Yeah.
I see no more questions. I want to comment, not meant as a criticism, but I think with verification source, people, I think maybe it's better to call it sort of pre-warning or whatever thing, right? Because I think one of the things that's interesting now is that data analysis people should wonder, what if there is a LISA source where upfront we know the distance and the masses and the sky position? Nobody, I think, has really wondered about that. They work very hard to get the sky position to alert EM people, but this is the reverse order. Anyway, thank you very much for this question. Let's thank Sheng again. And so we switch gears a little bit, at least in terms of, I guess, size and distance. We move to Sophia Yi from University of Virginia, talking about determining the individual masses of accreting white dwarf binaries. Please, Sophia, go ahead.
All right. So hello, everyone. I'm Sophia. I'm an undergraduate student at the University of Virginia. And today I'll be presenting my research with Professors Yagi and Aris on determining the individual masses of accreting white dwarf binaries. So the type of binary white dwarf systems we're looking at are depicted in this image on the right. We have a donor star, and although it's larger in size, it actually has a smaller mass. And in particular, we're considering donor white dwarfs with that are called really extremely low mass donor stars, which means they have this helium core and may or may not have a hydrogen envelope as well. But the picture to keep in our minds is that we have this extremely low mass donor white dwarf that is losing mass or accreting onto its binary companion, which I'll refer to as the accretor throughout the rest of this talk. And so when we first set out to do this research, we were really interested in just seeing if we could tell what the masses of this donor and the accretor star are using LISA's measurements of the frequency and frequency derivative of gravitational waves emanated by the binary. But along the way, we ran into some issues and ended up having to tweak our technique in a way that had us actually kind of add studies on the measurability of a few other white dwarf parameters. So I'll talk about that extensively in a bit, but just to begin, I want to describe our approach to the problem. So we begin with the understanding that the gravitational waveforms collected by LISA can be broken down into an amplitude, which I'll call A, times the cosine of a time-varying phase called phi. And the idea is that we can further break down A and phi into measurable quantities. So we're looking at the gravitational wave frequency derivative, so that's F and F dot, and then also the luminosity distance D and the chirp mass script M. And the idea is that the more that these parts, these measurable quantities in the waveform depend on white dwarf parameters, the better we'll be able to measure these parameters. So for instance, if we have a way to express the frequency entirely in terms of the donor mass, then anytime we receive LISA's measurements of frequency, we'll immediately be able to infer what the donor mass is. Now, of course, this is a very simplified picture. In general, F and F dot are going to depend on more than one white dwarf parameter. And so let's see what parameters they depend on. So expressing F and F dot in terms of these white dwarf parameters, what we do is we begin by considering the particular mass accretion mechanism that exists for these types of binary white dwarfs. So for the extremely low mass white dwarfs that we're considering, accretion occurs through what's called Rauschenberg overflow. So the Rauschenberg is what's shown here in the kind of light blue dot dash line. It's the outer limit at which matter is gravitationally bound to the white dwarfs. And what happens in Rauschenberg overflow is that the donor star expands over time due to evolutionary pressure, and it ends up filling its portion of the Rauschenberg and then kind of overflowing and seeping into the left portion where the binary companion is, and matter becomes gravitationally bound to the companion. And so if we have this particular mechanism, if we have Rauschenberg overflow or Rauschenberg filling, then we actually know that the donor star's radius will scale with the semi-major axis. And so we can throw this kind of proportionality into Kepler's third law, where we have the frequency is 2 over the orbital period. And then we arrive at a very simple expression for the gravitational wave frequency in terms of just the individual masses and the radius. Then what we can do is we can differentiate this relatively simple equation for F with respect to time to get F dot. And when we do this, because of the way that the radius and the mass are related, we end up introducing this new parameter called eta. And I'll explain a bit what eta means here. But the idea is now we have F and F dot in terms of just our our white dwarf parameters, the masses, the radius, and then eta. I'll mention that this expression for F dot assumes that no mass is lost from the binary due to shell flashes or anything like that. But yeah, so here we have F and F dot. But what is eta? So essentially, eta defines the response of our donor white dwarf to mass loss. And what I mean by that is that eta will tell us whether and to what extent the white dwarf will grow or shrink as we take mass away from it. So for the extremely low mass white dwarfs we're considering with these helium cores, eta depends very drastically on the stage of evolution we're considering. So in an early stage of evolution, The white dwarf has a helium core, but that helium core is surrounded by a thick hydrogen envelope. And what that hydrogen envelope does is that it causes the star to behave like ordinary matter, in the sense that as we remove mass from the star, it will shrink. So this kind of intuitive phenomenon of the radius decreasing as mass decreases corresponds to eta being greater than 0. And this is to be contrasted with the late stage of evolution, where the hydrogen envelope has been stripped away. All we have left is the degenerate helium core. And since this star is now degenerate, the radius will actually increase as mass is lost from the donor, and this corresponds to eta being less than 0. So what we expect then is that as the star transitions from an early to a late stage of evolution, this parameter eta is going to start at some positive number and then eventually pass down through 0 and enter the negative regime. It's worth mentioning, although the early stage of evolution doesn't last for nearly as long as the late stage, we're definitely still interested in studying this early stage of evolution, because this is when the emitted gravitational waves by this binary are expected to be largest. And so we have a greater chance of being able to detect white dwarf systems with donors in this kind of early stage of evolution. It turns out that considering this difference between the early stage and the late stage of evolution does more for us than just tell us what eta will be. And what this comes down to is the fact that in the late stage of evolution, we actually have an analytic mass radius relation given by P.P. Eggleton. And so because we have this mass radius relation, anytime we have a donor mass value, we'll also immediately be able to infer the radius of the donor star. And then because of the way eta is defined, we can rewrite eta as the mass over the radius times the derivative of the radius with respect to mass. And we have, since we have an analytic formula to throw into this derivative here, essentially what that means is that anytime we have a donor mass value, we'll also be able to immediately infer the radius and eta as well. It turns out that we can also immediately infer the gravitational wave frequency from just the donor mass in this late stage of evolution. This can't be immediately seen from the equations, but it was first observed in this paper by Breivik et al., where they simulated a bunch of these binary white dwarf systems with the extremely low mass donor stars, and they observed this universal relation between the donor mass and the frequency. And so what we did is we took the analytic mass radius relation from Eggleton, we threw it into the frequency expression that I derived on the previous slide, and we found that we were able to replicate Breivik's fit. And so their fit is showed in the dashed black line in the background, and then we have our plots of the donor mass with respect to frequency for a number of different accretor masses here, and we see that the curves all agree very well. And so what this means then, just to kind of summarize this slide, is that anytime we have a value known for the donor mass, we immediately will also know the radius, eta, and also the frequency. And so in this late stage of evolution, there's a really nice way to kind of tie together all these parameters and see how they're related to each other. And this can't be done in the early stage of evolution. So to begin with, we don't have an analytic mass radius formula for the early stage of evolution. And we thought, well, maybe we can find some way to relate the mass, the radius, and eta using experimental results. So we turned to MESA, which is a public stellar evolutionary code. And we started modeling a bunch of white dwarfs with helium cores and hydrogen envelopes. We tried different sizes of helium cores and envelopes and such. And we started trying to interpolate this data for the radius versus the strip mass, as well as eta versus the strip mass. Unfortunately, what we found is that it looks like the radius isn't computed to a high enough level of precision with MESA for us to be able to take the derivative. And we end up running into all this kind of very unphysical noise. And so what I plot here is the absolute value of eta on log scale. And so we see that eta starts positive like we expected. It dips down through 0, which is where the cusp is, and then enters kind of the negative regime. But then we run into all this noise. And it turns out that this is actually one of our better models. And often we would run into noise before eta even reached 0. And so what this means then, in terms of minimizing the amount of parameters we necessarily have to look at in our parameter estimation, is that in the late stage, it looked like we might be able to do our estimation with just 4 parameters: the initial phase, the 2 individual masses, and then the luminosity distance. However, since we can't relate eta, the radius, and the mass together very neatly in the early stage of evolution, we have to now include eta and the radius in our parameter set. And then, of course, since we want a very holistic view and we want to perform our parameter estimation for the early stage all the way into the late stage of evolution, we're going to have to use this larger parameter set. And so, as you can imagine, performing a parameter estimation with 6 parameters is going to be a little more difficult. Fortunately, one thing we may be able to do is eliminate one of these parameters. And specifically, we might be able to take away d as a parameter. And we could do this if we assume that the luminosity distance can be independently measured by a different detector like Gaia. And if that's the case, if we know d, then obviously we don't have to include it as a parameter. And then we have just this 5-parameter set. And I wanted to show this plot by Breivik et al., where they have estimated that there are a number of these kind of binary white dwarf systems with the really low mass donor stars that are expected to be detectable by both LISA and Gaia. And so it's not completely implausible that we would be able to remove d as a parameter. So now we have what our parameter sets will likely be, and I'm going to explain what the parameter estimation is that we did. So we really just performed a Fisher analysis, and the way that this Fisher analysis works is that we define the Fisher information matrix so that each of its elements are computed as the inner product between partial derivatives of the waveform with respect to each of the parameters of interest. And then what happens is when we invert this Fisher matrix and then take the square root of the elements, we receive back the uncertainty on our parameters. And so I'm going to show our results for the Fisher analysis for both the 5 and 6 parameter set, including and excluding d. But first, I just wanted to show this plot of the gravitational wave strain versus LISA's noise curve. So again, we have the noise curve from Robson et al. And the gravitational wave strain curves are the ones in the green, purple, cyan, and brown. They start where the orange arrows are pointing. They evolve up to the top right where they reach a period minimum. And then they enter the late stage of evolution, which is the kind of long tail extending down to the bottom left of the plot. And so what we see here is that, especially in the early stage of evolution, like I mentioned earlier, our gravitational wave strain is much higher than LISA's noise curve. And so we have a good chance of being able to detect the binary white systems, particularly in this early stage. So now we know that, yes.
3 more minutes.
Okay, thank you. So now we know that we should be able to detect the gravitational waves from these binaries. And then now that we know that, let's see what we can see with these gravitational waves. I'm first going to present our results for the 5-parameter set. Again, this is here where we assume that the luminosity distance has been independently measured. We actually assume that it's been measured to be 1 kiloparsec. Again, we use LISA's noise curve from Robson et al., assume a 4-year observation period. And then because we have so many parameters, we actually had to impose some Gaussian priors on the masses. And specifically, we have a 0.1 solar mass range for the low mass donor star. And then we believe that the accreting companion is likely to be a carbon-oxygen white dwarf that exists in the roughly 1.2 solar mass range. So with these as our assumptions, here are the contour plots that we get for the fractional error on the individual masses. What we have here, the way to interpret these plots is we're looking for a small fractional error, because a small error, of course, corresponds to being able to measure the white dwarf's masses to a higher level of precision. So we see that particularly in the blue and purple kind of region of parameter space, where the white dwarf and the where both masses are kind of higher masses within our range, we see that the fractional error is pretty small. And this means we have a very decent chance of being able to constrain the individual masses in these regions of parameter space. We find a similar thing for the radius and eta. In particular, eta looks very well constrained. We have very small or relatively small errors on the donor radius. And then the measurability of eta also looks fairly good if we focus on this kind of purple blue region of space again. And so to summarize our results with the 5-parameter set, as long as we know the luminosity distance and we impose the priors I showed, we have a very fair chance of constraining both the individual masses as well as the radius and eta. Now let's see what happens when we add d as a parameter into our set. So again, this is where we assume we don't know the luminosity distance independently. The rest of our assumptions are the same. And what we see,
one more minute.
Okay, what we see here is that unfortunately, when we don't know d, the parameter estimation simply returns the priors on the masses. So we gain no additional constraints on what the individual masses will be, which is unfortunate. On the bright side, as we can see here, the radius and eta are still relatively well constrained. In fact, if we compare it with the results for the 5-parameter set, we see that our error is about the same. It hasn't changed even though we added luminosity distance as a parameter. So to summarize our findings with the 6-parameter set, We are unfortunately unable to kind of constrain the individual masses in this situation. However, we are still able to measure the radius and eta to a roughly good extent. And then to summarize everything then, to wrap up what we're doing here, we used a Fisher analysis to estimate the measurability of a few white dwarf parameters, first the masses, and then we also ended up including the radius and eta. And what we found is that if we know the luminosity distance independently, we have a fair chance of constraining all 4 of these parameters. But unfortunately, if we do not know what the luminosity distance is, then although we can still kind of measure the radius and eta, unfortunately, we are no longer able to constrain the individual masses, the mass of the donor star and the white dwarf and the accreting star. So that's all I have for today, and I'd be happy to take any questions.
Thank you, Sophia. Well timed. Are there any questions? There is a question or more a comment in the chat by Dennis. Do you want to unmute and say the comment or ask a question?
Oh, yeah, it might or might not be a problem because the error in the Eggleton formula is about 2%, but it also fluctuates quite rapidly up and down as a function of mass ratio. So it's not a smooth approximation to the exact calculation. The power law, I mean, I'm not sure. The only way to tell is to use a more accurate formula and compare. It might not be a problem at all. I don't know what the other errors are. Maybe other errors are more than 2%.
Yeah, I'm not sure. We've only tried using Eggleton's formula. One thing we did is we computed eta with Eggleton's formula, and it came out to be roughly what we basically modeled a few curves, and when we used Eggleton to compute eta, it came out to be eta equal to -1/3, which is kind of what we expect. I guess that's kind of by definition that for Eggleton's formula, we have the cold temperature formula. I'm sorry, I don't know of any alternatives we could use that might be more accurate. But yeah.
Well, there are ones, but instead of power to the 2/3, you have slightly different powers or better. So you have a 2/3 and a 1/3, but it turns out that if you adjust those numbers, you can improve it. And then there's other ways, just by including more terms in the expansion, you can improve it too. But that might, if it's not just a simple power law, it might mess up the simplification.
Yeah, and I'll just say this is why we were interested in trying to use MESA to model like radius and mass curves, because ideally we'd be able to see what actually happens like from experimental data if the radius or if eta reaches -1/3 or some other value. Just being able to confirm that with MESA would be nice. So we're still working on that. We're still trying to tweak our approach with MESA, see if we can get rid of that noise.
Yeah, I think the mass radius is probably more uncertain for the comparative. Yeah, okay.
Let's wrap that up. There is a question, I guess, from the YouTube. Why is the blue-purple area your lowest errors? Please, could you go over that?
Sure. So that's really just a function of how I've the particular color plot function on Mathematica I use. It's just the color plot is just the scale we have. So the red corresponds to kind of the smallest fractional, or sorry, the largest fractional error. If we go 10 to the minus 0.35 is going to be a smaller error than 10 to the minus 0.05. So that's just
I think the question is, why are the blue areas in the regions where they are? You already explained it for the left one, I think, right? Because of the higher masses.
Oh yes. Oh, okay. Sorry. That makes more sense. Yeah. It's a function of. So really, what it comes down to is for the donor mass. When we have a higher donor mass, again, because especially in the late stage of evolution, it's really the donor mass that's determining the frequency. Then we're able to constrain these mass higher, to a higher level of precision. I will just show, I didn't have time to show this in our actual plot, but what we found is that we could actually trace where the error on the radius and eta and d were coming from. And if you look at plots of the derivative of the frequency with respect to the radius, or the f dot with respect to eta, and then we also include the SNR, we almost completely replicate the shape of these contour plots. And so what this means is that basically we know that the error on the radius and then eta and then d, those are all determined by different portions of the amplitude. So for radius, it's f and then SNR. If for eta, it's like f dot and then the SNR. And then for the luminosity distance, it's a question of how well we can constrain the amplitude. If we take the derivative of the amplitude with respect to d, that's where we have these kind of shaped contour plots.
All right, in view of the time, we have to wrap up. Thank you again, Sophia. And we move to the third talk of this session by Shuyan Lau, also from the University of Virginia, on the effects of dynamical tides on gravitational wave signals from eccentric double white dwarf systems.
Right. Thanks for the introduction. So, hi everyone. I'm Shuyan Lau. I'm a PhD student from the University of Virginia as well, and I'm from the same research group as Sophia. I'm also working with Professor Phil Aris and Ken Yagi. Today, I'm going to share with you this project we have been working on, and about the effect of dynamical tide on the gravitational wave signal from eccentric double white dwarf systems. So we are kind of wrapping up right now and writing a paper. And if you are interested in this topic, please stay tuned. So first of all, I would like to talk a little bit about the motivation of this project. So in this project, we focus mainly on detached eccentric double white dwarf systems within the LISA frequency band. And we want to study the effect of dynamical tide on orbit and hence the waveform. In particular, what we find is that the dynamical tide has two main effects on the orbit. First one, if the dynamical tide effect is perturbative on the background orbit, then it will cause the orbit to have extra orbital precession. And for orbits with higher eccentricity and small separation, we find that the dynamical tide kind of drives the orbit into chaotic motion, which completely alters the waveform. So why are we interested in these eccentric systems? So as we all know, this galactic double white dwarf systems is one of the most promising guaranteed sources for LISA. We're expecting around 10,000 of these systems to be detected. However, most of them, due to their formation method, they're kind of circularized before they even form. So in order to have these eccentric systems, we require multiple body interactions or dynamical interactions. And these have been studied by some previous literature. For example, for these ones by Ivanova et al. Or Williams et al., they have estimated the eccentric double white dwarf systems come from the globular clusters within our galaxy, and they're expecting at least a handful of these systems to be detected by LISA. And for multiple body interactions, unfortunately, these populations are kind of poorly constrained. But within these systems, there is the so-called Quasar mechanism that drives the system into high eccentricity and forming eccentric double white dwarf systems. So what makes these eccentric binaries interesting is that they have a very different waveform from the circular ones. As illustrated in this equation here, the waveform basically composed of a sum of harmonics. And as illustrated in this plot in the frequency domain of the waveform, basically the waveform of an eccentric binary consists of a sum of harmonic represented by each peaks here, and they have the eccentricity dependent amplitude, and also a precession term in the waveform, which splits each harmonic into 3 different submodes. And by measuring the relative amplitude of these harmonics, we can know the eccentricity of the orbit. And by measuring this splitting, we can know the precession of the system. So this is actually discussed before in a study by Williams et al. In 2008, which they consider the precession due to various non-Keplerian forces on the eccentric double white dwarf systems. And in particular, they considered 3 different effects: the tidal effect, the leading post-Newtonian effect, and also the rotation effect. for the equilibrium tide effect, they consider the formula using the tidal love number, which the equilibrium tide depends linearly on the tidal love number and have a 1 over the separation dependence to the 5th order. And by measuring this tidal precession, one may actually infer some information about these tidal parameters, which it depends on the internal mass distribution inside the white dwarf. So the thing about this equilibrium tide formula is that it's basically the static limit of the general tidal problem, which has ignored the dynamical tide. So this kind of motivates us to think about what the dynamical tide can give us inside the eccentric double white dwarf systems. So now, in order to solve for the dynamical tide, we'll have to consider the full tidal problem, which basically we have to solve simultaneously the equation of motion for the fluid element within the star, and also after the deformation, the extra force that the deformed star gives to the orbit. So in order to solve the problem, we'll need to solve for the deformation factor C, and a useful method is to decompose it into a spaces formed from its eigenmode with eigenfrequency omega alpha. In order to simplify our calculation, we consider only the dominant mode, the so-called F mode, which has the largest overlap integral with the tidal interaction. Right. So with this approximation, we consider the equation of motion with the addition of this F mode contribution. And as discussed earlier, this dynamical tide can actually cause the system to evolve chaotically. And this is the earliest study is by Martling in 1995, and there are also later studies of it. And here I'm not going into too much details into it, but I'm just going to use the method by Ivanov in 2004, which estimates the region of the parameter space in which this dynamical tide can drive the system into chaotic motion. So here I'm showing the parameter space formed from the pericenter separation, RP, in a unit of Roche filling distance, such that the system still remains detached. And the x-axis is the eccentricity of the orbit. So in this approximation, we can see for different masses, for system with different masses, we can have different boundary for the transition for the system to go from periodic motion into chaotic motion. And here I'm using a integration of the orbital equation of motion at this particular point to show that a system with this initial parameter will have a chaotic system, which orbital frequency basically changes over time with a increasing number of pericenter passages. So in the following, we mainly focus on the periodic regime, and actually within our method, we basically assume our orbit to perform a periodic motion in order to simplify our calculations. So now we assume that the orbit itself is periodic, and in order to solve for the equation of motion for the tide, we assume a Fourier series solution of the tidal excitation amplitude, which resembles the solution of a simple harmonic oscillator. So basically, it depends on an amplitude term that is in the form of a Lorentzian, which we call as the mode amplitude factor, and basically is represented as a Fourier series of a sum of harmonics. So in this expression, we can see that if the orbital motion is slow compared to the frequency of the F mode, that is the orbital frequency is much smaller than omega alpha, then we can take the leading order expansion, and this expression basically reduces back to 1, which gives us the result of an equilibrium tide. And if we subtract this 1 of the full expression, then we'll have the so-called dynamical tide effect of the tidal interaction. So from that, we can obtain an expression for the precession. So basically, we write it in terms of a sum of harmonics with this mode amplitude factor given in the previous slide, and also a overlap integral that is given for F mode. And it also depends on some function of eccentricity and some power of the orbital separation. And as an example, I'm showing one orbit with equal mass 0.6 solar mass and eccentricity of 0.5 for the precession rate of the system as a function of orbital period. And I'm showing both the contribution from dynamical tide and the rest of the effect, including the equilibrium tide and the first post-Newtonian effect. As we can see, in this dynamical tide contribution, there are multiple crossings of the resonance in which the higher harmonic basically goes near the F mode frequency at this region. And other than that, the off-resonance part of the dynamical tide basically has a smaller contribution than the equilibrium tide and the 1TN correction. And if we look at the off-resonance part, we can see that this off-resonance part basically goes as 1/8 to the 8th power, in contrast to the equilibrium tide, which means it is much steeper. So we want to know how much this off-resonance tide can cause the effect to deviate, because the resonance effect is so narrow here. So we first want to look at the off-resonance part. To do that, we take the approximation of our mode amplitude factor to the leading order, which ignores the effect of resonance. And we want to maximize the previous formula for the precession by choosing a certain set of parameters. First, for the separation, we want it to be at Roche loop filling. And for the eccentricity, we set it to 0, such that the system is always at its closest distance. And for the mass ratio, we set it to 1, as shown on the plot on the right-hand side. When the system is at equal mass, both the equilibrium tide and dynamical tide takes the maximum value. And what we find is that this dynamical tide can have potential to give a 25% of difference compared to the equilibrium tide, which means if we have ignored this defect in the parameter estimation, then this is going to cause quite a significant systematic error in the analysis.
Julian, 3 more minutes.
Okay, thanks. So now we want to look at the resonance part of the tide. So basically, we can see from the previous plot that this resonance peak are kind of narrow, but they increases, the width of resonance basically increases when the system goes closer to each other. So we look at the width over space ratio, which is defined by delta FR by delta FS. Basically, delta FR is the region in the frequency space which the dynamical tide contribution from a single mode exceeds that of the equilibrium tide. And for the delta S here, it's basically the spacing between each subsequent resonance. So as we can see from the plot on the right-hand side, if we plot this ratio for systems with different eccentricities as a function of the orbital frequency, we can see that this ratio basically increases with the orbital frequency as we expect. And for systems with higher eccentricity, this ratio also increases because this spacing between each subsequent resonance basically decreases when we have higher eccentricity. And one thing that we have ignored in this analysis is that we have set the system to be periodic, kind of artificially. So if we look back into the chaotic boundary plot, you can see that some of the systems here shown here are basically within the chaotic regime. So basically, some of the systems will have a completely different waveform from the others that are periodic and precessing. So here, I'm going to give a summary of the results here. So basically, what we find is that the dynamical tide becomes more important when the system is at close separations. In particular, for the systems we've considered here, that is the equal mass 0.6 solar mass systems, this dynamical tide start to become important when the orbital period is less than 10 minutes. And for the specific details, we look at the off-resonance piece of the dynamical tide and find that it has potential to contribute up to 25% of the overall precession. And this effect kind of increases for systems with smaller eccentricities. On the other hand, for the resonance response, we find that it takes up to around 10% of the frequency space when the system is at close separation. And this effect increases when the system has larger eccentricity. And lastly, we also show that for certain systems with high eccentricity and small separation, it basically transits into a chaotic system, and this completely alters the waveform. So, lastly, I'm here just showing one example of the chaotic waveform within the circuit region I showed earlier, and we can see that the frequency domain chaotic waveform basically has a non-zero frequency power, non-zero power at any frequency in between each harmonics, in contrast to a periodic waveform which contains only the equilibrium type. However, this waveform still consists of the same, still have the same shape in terms of the profile inside the frequency domain. So basically, this is the end of my presentation, and I'm happy to take any questions. Thank you.
Thank you very much, Julian. So let's see if there are already questions. I don't see anything in the chat. I see lots of clapping hands in the participant list, but no hands up. Anybody? In the meantime, I can ask a question.
Sure.
How much does the this effect of the dynamical tide depend on the properties of the white dwarf? And how do we know the properties of the white dwarf well enough?
So basically, the properties of the, say, the internal structure, the composition of the white dwarf enters through this overlap integral. So in this formula, we can see that the precession basically goes as the overlap integral to the power of squared, to the squared, and and basically we have actually done a plot of, I haven't shown it here, but overlap integral basically has a slow varying function in terms of the mass of the white dwarf. So it is like kind of a constant. So I mean, it has a range of around 0.1 to around 0.2 in terms of the magnitude. So it is more or less a constant. And yeah, this is what I can say about how this precession depends on the composition of the white dwarf itself. Oh, it also enters through the F mode frequency here as well. But if we are looking at the so in this analysis, we have only focused on the fundamental mode, but the composition of the white dwarf also causes other classes of mode, like the gravity modes, G modes, and some sort of that. If we want to measure these quantities, we will need to include also the other classes of mode into our analysis as well, which we have ignored here. So I'm not sure if that answers your question.
Yeah, no, thank you. I think I have a follow-up question, but let me first see if there are other questions. I don't see any hands. I don't see anything in the chat. And so the follow-up is basically, indeed, do we know this well enough? And the background is that I know from the work I've been involved in these interacting binaries that it's not so obvious whether the accreting white dwarf will be tidally locked in the orbit, yes or no, because the viscosity of the white dwarf is so poorly known. And so my question was, this uncertainty, does it impact your work?
Oh, yeah, sure. And it's actually something we are still looking at right now. So, so near the resonance, depending on the viscosity of the system can actually be locked at near the resonance. And this is something we really want to know right now, whether it is possible for this higher harmonics to be locked within the F mode frequency. but currently we still don't have any result for that. So yeah, this is still an unknown for us.
All right, thank you. We may have gone a bit too technical for some of the audience. Let me see. Final call for questions. If not, let's thank all the speakers of this session again.
Thank you.
And so this brings us to the end of the first part of the Astrophysics with Lisa second parallel session. We now have a short break. Apologies, kids are playing outside, so you may hear some shouting. But we reconvene again 15 minutes from now with another 4 very interesting questions. Thank you all and see you back in 15 minutes.